Hi there, Mr. Sutton here, bringing you the AB Calculus 512 Extra Practice number 3 solutions on FTC free response practice. For this free response question, we have a continuous function f and a whole bunch of information about this function that they gave us a graph for that might be relevant later on. For the first part of this problem, we want to know if f is differentiable at x equals 0. And then here's the kicker. You have to use the definition of the derivative with one-sided limits to justify the answer. So we can tell by looking at the graph, which is the graph of f here, that f is not differentiable at 0. We have a pointy spot on the graph at 0. Whether you want to call that a corner or a cusp, either way, we know that we're not differentiable there. But we have to use the definition of the derivative, which is that limit definition, to actually show that here. So in general, that limit definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we plug in 0 and take the left-sided limit to start with, I can write limit as h approaches 0 from the left of, this would be x plus h, but because x is 0, we're just writing f of h right here, minus f of 0 over h. So this is saying the left side limit of the slope as I approach 0. Well, what is that? I mean, if you just try to do this using limits and functions and whatnot, that's going to be a little tricky. It's easier just to look at the graph and ask, okay, what is the slope of this thing as I approach 0 from the left side? Well, as I approach from the left side, I'm using this straight line here, which has a slope of, let's see, we're going up 2 and over 3, so a slope of 2/3. That is our left side limit as we approach 0. How about the right side limit? So I'm going to write this as h approaches 0 from the right of pretty much the same stuff I wrote over there. And what does this come out to? Well, the slope coming from this side, it's a little bit tougher to tell because this is not just a line. This is a curve, and there isn't really a good formula to use to figure this out. But what we can tell just by looking at the graph, and nobody can really contradict us on this, is that that slope is going to be negative. You're going down as you approach from the right side. So we can say this is less than 0. If it's less than 0, that means there's no way it can match a positive number like 2/3. So this means that the overall limit as h approaches 0 of this stuff does not exist. Therefore, since that limit does not exist, since the slopes don't match up, that tells us that f is not differentiable at x equals 0. For this problem, we're asking how many values of a on the interval from -4 to 6, and note that we're including -4 but not including 6. On how many values on this interval is the average rate of change of f on the interval from a to 6 equal to 0? This seems kind of tricky, and like, you have to kind of guess and check in a whole bunch of places, but let's see what's really going on here. For the average rate of change to be 0, average rate of change is just y2 minus y1 over x2 minus x1. It's basically 2-point slope. That fraction only comes out to 0 if the numerator is 0, and the numerator is only 0 if the two y values you're subtracting are the same y value. We already know, sort of kind of, one of the y values. We know that it's going to be whatever f of 6 is. So we just need to figure out an x value such that plugging it in gives me the same thing as f of 6. So in general, a-rock is going to be 0 where f of a equals f of 6, and f of 6, looking at the graph, has a value of 1. That was like the 1 point that they gave you. So a quick way of figuring this out is just to see how many places on the graph we cross a horizontal line that goes through the y value 1. Anything that this line touches, this is going to be a spot where the y value, by plugging in your a value, comes out to 1. So how many places does this happen? Well, let's see. We've got 1, 2, and is this a third spot? Does this count? It doesn't, because they said how many a values where we're not including 6. So that means there's only 2 places on the interval from -4 to 6, including -4, not 6, where this happens. So there it is. For this part of the problem, we're asking if there's an a value between -4 and 6 for which the mean value theorem applied to the interval from a to 6 guarantees a c value such that f prime of c equals 1/3. All right, so this one is kind of tricky. Normally with a mean value theorem problem, they give you kind of a set interval and you just have to find the average rate of change over that interval and show that it matches some instantaneous rate of change, you also have to show differentiability and continuity. So it's not like it's an easy thing, but here we're dealing with a moving target, this a value. So a could be anything on the interval from -4 to 6. So they're asking, is there any kind of starting point for this interval where if I use that interval with the mean value theorem, good things happen? All right, well, let's eliminate some things that can't possibly work out here. So mean value theorem requires differentiability on whatever interval this is. And we know that we are not differentiable at x equals 0. So that means that nothing before x equals 0 is going to make this situation happy, because you're going to be including this non-differentiable spot, and then the mean value theorem guarantees nothing. So for anything to work, for any a value to work, it's got to be an a value between 0 and 6. Well, the next hurdle we have to pass is what a value, if I use that as my starting point of the interval, is going to give me an average rate of change of 1/3. Certainly not 0, 2. The average rate of change between this point and this point, I mean, without even calculating it, we know it's going to be a negative average rate of change, so it's not going to be positive 1/3. What other point is there on this interval that we could possibly use? The only other point they gave us, and this is just kind of using the structure of the problem to speed things along, the only other point that we have on this whole interval, other than 6, 1, is this point right down here, this x-intercept 3, 0. Well, hey, this gets me to thinking, what is the average rate of change between 3, 0 and 6, 1? Well, we're going up 1 and over 3. That's a slope, if we were to draw a line between these two, a secant line, a slope of 1 over 3. So that would actually give us the instantaneous rate of change slope of 1 over 3. So we kind of know where this is heading. We want to say, yes, there's an a value that makes this work, and it's the a value 3. So that's where we're going, but we still need to justify it using the language of the mean value theorem. So let's start with our conditions for MVT, which are that we must have a continuous interval on a closed continuous interval and a open differentiable interval. So we want the interval from 3 to 6. We know that that interval is differentiable because they told us in the problem that on the interval from 0 to 6, the function f is twice differentiable. Well, if it's twice differentiable on this whole interval, it's certainly at least once differentiable on a smaller set of that interval. So we've got differentiability. We also have continuity on the interval from 3 to 6, the closed interval. How do we know that? Well, the very first line in the problem stem here tells us that a continuous function f is defined on the interval -4 to 6. So this is just, again, a small piece of that larger continuous interval. So we have the conditions of the mean value theorem. The conclusion of the mean value theorem says that there will then be an average rate of change, or there will be a c value where plugging it in gives you an instantaneous rate of change equal to the average rate of change on this interval. So next thing we have to do is actually show some calculations for the average rate of change. That's going to be f of 6 minus f of 3 over 6 minus 3. Now f of 6, looking it up here, that's 1. F of 3 is 0. So this is 1 minus 0 over 3, which just comes out to 1/3. So since we have shown that the average rate of change is 1/3, we've met our burden of proof, and there is indeed some c value on the interval from 3 to 6 where f prime of c equals 1/3. And the NVT guarantees this. For this last problem part, they're defining the function g as the integral from 0 to x of f of t dt on interval from -4 to 6. We want to know on what intervals in that interval is the graph of g concave up. Okay, so this is one where they gave you some information in the problem that was actually kind of misleading, because if you look up here, they say f double prime of x is greater than 0 on the interval from 0 to 6. And you look up here and you're like, wow, it really is greater than 0. F is concave up on the interval from 0 to 6. But before you put 0 to 6 as one of your answers, look at what they said here. They asked where the graph of g was concave up. And g is not exactly the f function. G is the integral of the f function from 0 to x. So this was kind of put in here to mislead you. It actually serves no other purpose in this problem than misdirection. Shame on them. So how do we get to the bottom of this one? Well, if we want to know where g is concave up, One way of doing that is certainly to figure out where g double prime is positive. Another way, which might be a little bit easier based on what we have in the problem to work with, is figuring out where g prime is increasing. Well, what is g prime of x going to look like? Using my fundamental theorem on this equation they gave me right here, I can say g prime of x equals just f of x. We're just plugging this x in for the dummy variable here. So that being the case, where is f of x, also known as g prime of x, increasing on our graph? Well, here's the graph of f. We can just look and see where this thing is going up. F is going to be increasing from -4 to 0, and then it stops at 0. But then it starts increasing again once we get to 3. From 3 to 6, we are also increasing. Since g prime is increasing on these intervals, it follows that g is concave up on these very same intervals. For this free response problem, we're given the graph of f, and we're also told that the g function is the integral of f from 2 to x. First task is to figure out if g has a relative min, max, or neither at x equals 10. All right, well, if I want to figure this out and justify it, I basically need to talk about whether g prime is changing sign at x equals 10, and if so, in what direction. Well, what is g prime? G prime, using our fundamental theorem here, is just going to be the integral of the derivative of this interval here, which basically means we're plugging the upper limit in for the dummy variable. So to put it simply, g prime of x is just going to equal f of x. Where does f of x change sign? A few places, but not at 10. At 10, we are about to cross the x-axis, but then f changes its mind and heads on back. So since f does not change sign at x equals 10, since g prime does not change sign at x equals 10, therefore g, the graph of g, which they didn't show us, has no relative extrema, no mins or maxes at x equals 10. For this part of the problem, they want to know if the graph of g has a point of inflection at x equals 4. Well, to figure out if g has a point of inflection, one way to do it is to figure out if g double prime is changing sign. Another way to do it is just to figure out if g prime itself is reversing direction, changing either from decreasing to increasing or increasing to decreasing. Recall that g prime of x is just f of x. And f of x, just looking at the graph here, is reversing direction at x equals 4. Specifically, f of x is changing from increasing to decreasing at x equals 4. Therefore, we can conclude that g has a point of inflection at x equals 4. On this problem, I want to find the absolute min and max for the graph of g on this interval. So using the candidates test, I'm going to have to test out -4 and 12. I always have to test out the endpoints. I'm also going to have to test out some of the critical values, specifically the ones that could be mins or maxes. So those would be ones where you have a sign change in g prime. So let's talk about critical values then. G prime, which we already said was really just f of x, changes sign only at x equals -2 and x equals 6. So those are the only two critical values we actually need to test with our candidates test. 2 and 10, although those are critical values, places where g prime is 0, there's no sign change there, so those can't be mins or maxes. All right, so let's test out, let's start with -4, just plugging these all into the g function now. We're going to be doing a lot of geometry, a lot of work with triangles, it looks like. So we have the integral from 2 to -4 of the f function. So we're integrating backwards at this point. So we have this triangle area down here that we have to start with. We have 1/2 times a base of 2 times a height of 4. This would normally be negative, but since you're going from right to left, this is actually going to be a positive area. So we have 1/2, so positive 1/2, base of 2 times a height of 4. Next, we have this triangle here. This is going to be 1/2 times a base of 4 times a height of 4. This would normally be positive, but again, you're going backwards from 2 backwards to -4. So we're going to have to subtract all that. And what does all this come out to? Let's simplify it so we can compare it easily. So the 1/2 and the 2 cancel. This is just a 4 over here. Over here, this is going to be, let's see, half of 4 is 2. 2 times 4 is 8. So basically 4 minus 8, which is -4. Let's keep going now. We're going to do g of -2 right here. So this is just using this negative triangle area from our first little exploration there. So this is just going to come out to -8. So that was a little easy because we already kind of found that area before. Next we need to do, let's see, from 2 to 6. 6 is our next critical value. And I'll just do that up here because I ran out of space down there. So going from 2 to 6, we have, this is actually going to be positive area now because we're going from left to right. And this triangle, this is just 1/2 base of 4 times a height of 4. So this comes out to +8. And then finally, the endpoint 12, this is just going to be the area I've already acquired from 2 to 6, which we said was 8, plus a little bit more, plus the area from 6 to 12. Well, that area we're going to be subtracting a triangle with a base of 4 and a height of 4, so -1/2 4 times 4. And we have another negative triangle here. This is going to be -1/2 base of 2 times a height of 4. So we've basically got 8 minus 8, so that cancels. And then the rest of this just comes out to -4. All right, so comparing these, we have, let's see here, we have -4, -8, +8, and -4. Let me start by identifying the absolute max. I've got to pick one of them. The highest number here is 8. It's actually the only positive number, so kind of by default, it's the max. And then the min is going to be the most negative number out of these. That's this -8 that we found at x equals -2. So there we go. They didn't ask us to tell them what x values these happened at, so we're done. For this part of the problem, they want to know for what x values on the interval -4 to 12 do we get g values that are less than or equal to 0, so non-positive, so 0 or smaller. All right, well, we already found before that g of -4 had a value of -4. That was back in part C. So just going from left to right, let's just start adding or subtracting areas and see where we end up with negative numbers. So as we go from -4 to -2, we're picking up some negative area here. This is going to be, each of these triangles had an area of, this half triangle had an area of 4. These bigger triangles have areas of 8. So we're losing 4 right there to get to g of -2. So we're down to -8 at this point. So this whole interval is negative. Now as we add this positive area, we're still not positive overall. We're adding 8 over the course of this whole triangle to get to g of 2. At that point, once we get to x equals 2, we've canceled out all the negative area. But on this whole interval from -4 to 2, we were negative until we got to 2. Now after 2, we're adding some positive area. To get to g of 6, you're doing 0 plus another 8, so that keeps you positive. From 6 to 10, you're losing 8 for area. But on that whole interval, you're still positive until you get to 10. Once you get to 10, where you're at a value of 0 again, then we're getting more negative area, 4 specifically. G of 12 is going to be 0 minus 4, so -4. So then we're negative again on the interval from 10 to 12. So just to review, we started negative. We were negative until we got to 2. So that's an interval of -4 to 2. Then we had some positive area. That positive area got canceled out over the course of this whole interval, and we didn't turn negative again until we got to 10. So from 10 to 12 was our other interval of non-positivity.